welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communication systems. Alright, we are currently looking at the process of estimating or process of computing the LMMSE estimate or the MMSE estimate of a MIMO, that is a multiple input multiple output wireless communication system. That is a wireless system which has multiple transmit antennas, both multiple transmit antennas as well as multiple receive antennas. That is why it is known as a multiple input multiple output wireless communication system, and the channel over which the communication takes place is known as the multiple input multiple output wireless channel. Alright. So, we have derived the LMMSE estimate as well as the estimation of the covariance for LMMSE estimation. Alright. Let us now do a simple example to understand this better. Alright. So, in today's module we are going to do an example for the LMMSE or MMSE estimation. Example for LMMSE / MMSE estimation of a MIMO wireless channel. LMMSE or the MMSE estimation of a MIMO wireless channel. Okay. Let us consider a 2 cross 2 MIMO system. For this purpose, consider a 2 cross 2 MIMO channel or basically a 2 cross 2 MIMO system. 2 cross 2 MIMO channel implies, that is, if you look at this, that is your, remember this is an M cross R where M is equal to 2, that is your number of transmit antennas, is equal to 2, number of receive antennas, that is your R equal to 2, which is the number of receive antennas. So, we have a 2 cross 2 MIMO system, it is M cross R, M is the number of transmit antennas, R is the number of receive antennas. This is a 2 cross 2 MIMO wireless channel. Okay. Now, let us consider n equal to 3. Alright, in this particular example, let us say we have n equal to 3 transmitted pilot vectors. Okay, we have n equal to 3 transmitted pilot vectors. Let them be x bar 1, that is the first pilot vector, that is 10, 8, x bar 2, that is the second pilot vector, that is 8, comma 10, x bar 3, that is the third pilot vector, that is 6, 6. Okay. So, we have 3 pilot vectors that are transmitted. Therefore, now from this 3 pilot vectors, remember capital N is the number of pilot vectors that we are considering. From these 3 pilot vectors, we will construct the pilot matrix. Therefore, the pilot matrix X therefore, the pilot matrix X is X equals, the pilot matrix is x bar transpose 1, x bar transpose 2, x bar transpose 3. The pilot matrix is your 10 comma 8, x bar transpose 2, that is 8 comma 10, x bar transpose 3, that is 6 comma 6, and this pilot matrix, remember this pilot matrix is a n cross m pilot matrix. Alright, n is equal to 3, M is equal to 2. So, pilot matrix X n cross M, that is your 3 cross 2, that is a 3 cross 2, that is matrix of size 3 cross 2, that is a pilot matrix X, capital X denoted by capital X is of size 3 cross 2. Okay. Now, now since we have 3 transmitted, n equal to 3 transmitted pilot vectors, we will have n equal to 3 corresponding received pilot vectors. Now, observe that we have 2 receive antennas. So, each received vector will be of size 2, because on each receive antenna we will have a symbol on each receive antenna, alright. So, each receive vector will be a vector of size 2, that is a 2 cross 1 vectors, and we have n equal to 3 such vectors corresponding to 3 transmitted pilot vectors. Okay. So, let the corresponding received vectors, let the corresponding n equal to 3 received vectors be let the corresponding n equal to 3 received vectors let the corresponding n equal to 3 received vectors be, we have y bar of 1, this is equal to, you let us say 2 1, y bar of 2, that is the second received vector is 1 2, and y bar of 3, that is equal to 1 1. Okay, that is n equal to 3 received vectors. Now, therefore, from this received vectors we can construct the observation matrix. Therefore, the observation matrix therefore, the observation matrix is y equals y transpose y bar transpose 1, y bar transpose 2, y bar transpose 3, that is the observation matrix, which can be written as y bar transpose 1, that is 2 comma 1, y bar transpose 2, that is 1 comma 2, y bar transpose 3, that is 1 comma 1. This is your observation matrix, and remember this observation matrix is n cross r, that is 3 cross 2, where n equals number of pilot vectors, r equals number of received or observed vectors. So, this is an n cross the pilot matrix X, this is an n cross R matrix, alright. So, this is corresponding to the MIMO system model that we have derived earlier. Remember, from the MIMO system model, recall that the MIMO system model is recall our MIMO system model is y equals x h plus v. This is our MIMO system model, where y is n cross r, that is in this case 3 cross 2, x is n cross m, in this case again 3 cross 2, h is m cross r, in this case 2 cross 2, and v is again n cross r, in this case it is a 3 cross 2 matrix. This is our, remember this is our MIMO system model, that is the multiple input, multiple output wireless channel model. Okay. Now, let the channel coefficients be IID, let us assume IID channel coefficients with prior variance sigma h square with identical prior variance sigma h square. Let the channel coefficients be independent be IID, that is independent identically distributed, that is independent identically distributed with each having prior variance. Remember, they are denoting the prior variance. This prior variance we are denoting this by sigma h square, or let us say dB prior variance sigma h square equals minus 6 dB. Alright, the prior variance sigma h square is minus 6 dB, implies if you look at 10 log 10 sigma h square, that is equal to minus 6, implies sigma h square is 10 raised to power minus 0.6 equals 10 raised to the power of 0.3 to the power of minus 2, and we know 10 raised to the power of 0.3, this is approximately equal to through 2, because 3 dB is approximately 2. So, this is 2 raised to the power of minus 2 equals 1 by 4. So, we have prior variance in dB sigma h square, which is minus 6 dB, which approximately this is 1 by 4, that is sigma h square for each IID channel coefficient of the channel matrix H is 1 by 4. Okay. Now, let us look at the noise variance. Let us assume that the prior noise variance, or not prior noise variance, but rather the dB noise variance equals 3 dB. This is straightforward, this is 10, because we know 10 log 10 sigma square equals 3 dB, or rather 3. This implies sigma square equals 10 to the power of 0.3 equals 2, because we know 3 dB corresponds to 2. Okay. So, sigma square, that is the noise variance, that is the noise variance per noise element, that is the noise variance sigma square per noise sample on each receive end. Remember, we are assuming, and we have gone through this when we discussed the noise rate, this is a noise variance per noise sample on each receive antenna. Per noise sample on each receive antenna, that is equal to 2. Okay. Now, let us compute X transpose. Okay. Now, first let us simplify the LMMSE channel estimate, LMMSE channel estimate. Now, we have to compute the LMMSE MIMO channel estimate. Let us compute, remember the LMMSE MIMO channel estimate, LMMSE of course if it is non-Gaussian, MMSE if it is Gaussian, that becomes your H hat equals sigma H square X transpose X plus sigma X H square identity of size m cross m inverse into X transpose Y. We will just simplify this a little bit. I remember I can write this also as sigma h square. In this term I can take sigma h square, in term inside brackets I can take sigma h square sigma square common. So, that becomes x transpose x divided by sigma square plus I m divided by sigma h square inverse into x transpose y. Now, when the sigma square comes out of the bracket, because there is an inverse, it goes into the denominator. So, I have sigma h square divided by sigma h square into sigma square, that becomes 1 by sigma square x transpose x divided by sigma square plus I m divided by sigma h square into x transpose y. Okay. And now, I can write this as bringing the sigma square, just for convenience, bringing the sigma square beneath x transpose y. I can write this as x transpose x divided by sigma square plus I m divided by sigma h square inverse into x transpose y divided by sigma square. Okay. This is just an equivalent way of writing this, because it is going to be convenient for us in the future. Now, what I am going to do is I am going to divide and multiply by r the number of receive antennas, and what that is going to give me is this is x transpose x divided by sigma square into I m divided by sigma h square inverse into x transpose y divided by r sigma square, and I take the r in the numerator, because I divide and multiply by r. The multiplied r I take inside the inverse. So, it again comes in the denominator, that becomes r in the denominator. So, that becomes x transpose x. So, the final expression for the MIMO channel estimate becomes just an equivalent way of writing it. It is x transpose x divided by r sigma square plus I m divided by r sigma h square inverse into x transpose y divided by r sigma square. And I am saying this is particularly convenient, because if you look at this part is nothing but the covariance of the MIMO this is the covariance, this x transpose x by r sigma square plus I m, that is identity of size m cross m divided by r sigma h square inverse. This whole part is nothing but the covariance of the estimation of the MIMO channel matrix. So, one need not recompute the covariance all over again, it just one can use this part that is computed for the LMMSE estimate, reuse it for the covariance, alright. So, that it is just convenient, because it saves some computation, it saves some computational burden. Okay. And remember again, r, this is nothing new, r is the number of receive antennas, that you should be well aware by now. R equals the number of receive antennas in the MIMO system. Now, let us start computing each of these quantities. Of course, we need x transpose x, remember the. So, let us start by computing x transpose x. X transpose is the transpose of x. Of course, you take x, make the rows into columns, columns into rows, that becomes x transpose. X is a 3 cross 2 matrix. So, x transpose is naturally this is going to be a 2 cross 3 matrix times x, which is basically your pilot matrix 10 8 8 10 6 comma 6. This is your pilot matrix x. This becomes your 200, 196, 196, 200, and now observe that the LMMSE estimate. Now consider the term x transpose x by r sigma square plus m cross m identity, that is 2 cross 2 identity, divided by r sigma h square, which in this case 1 over r sigma square 1 over r into sigma square is 2, r equal to 2, sigma square equal to 2 into x transpose x, that is 200, 196, 196, 200 plus 1 over r sigma h square 1 over 2 into sigma h square is 1 by 4 times identity 2 cross 2 1 0 0 1, and this will be basically your, if you compute this will be basically 50, 49, 49, 50 plus 2 0 0 2, that is your 52, 49, 49, 52, and therefore, now we compute the inverse of this quantity x transpose x divided by r sigma square plus I divided by r sigma h square inverse, which becomes, now it is a 2 cross 2 matrix. So, the inverse is easy, 1 over the determinant, which is 52 square minus 49 square times, interchange the diagonal elements of same. So, no effect, 52 52 of diagonal elements, take the negative, minus 49 minus 49. So, this becomes basically 1 by 3 times 101 into 52 minus 49 minus 49 52. Okay. So, this becomes 1 over 3 times 101 to 52 minus 49 minus 49 52. This is the expression for the matrix x transpose x divided by r sigma square plus identity matrix size 2 cross 2 divided by r sigma h square whole inverse. Okay. Now, we will compute the other component, which is x transpose y, alright, and then you have to multiply by x transpose y divided by r sigma square. Okay. So, now let us compute the other component x transpose y. This is again x transpose, which is a 2 cross 3 matrix, 10 8 8 10 6 6 x transpose into your observation matrix y, 2 1 1 2 into your observation matrix y, which is 34 32 32 34, and therefore, now your MIMO channel estimate is given as h hat equals x transpose x given by r sigma square plus I m divided by r sigma h square into x transpose y divided by r sigma square, which is equal to 1 over 3 into 101 52 minus 49 minus 49 52. This is your matrix x transpose x divided by r sigma square plus Im divided by r sigma h square inverse times, of course, we have to have the other part which is 1 over r sigma square 1 over r into sigma square. This is of course r, this is your sigma square which is corresponds to 2, which corresponds to 3 dB x transpose y, which is basically 34, 32, 32, 34. This is of course your matrix x transpose y, and now you put this all together and what you get is 1 over 12 times 101 into 200 minus 2 minus 2 200. Now, approximating this 101 as 100, what I am going to get is this is approximately equal to 1 over 12 into 100 to minus 200 minus 2 minus 2 comma 200, and if you look at this, this will be equal to basically you can see this will be equal to minus 1 over 6, or this will be equal to, I am sorry, 1 over 6 minus 1 over 600 minus 1 over 600 1 over 6, and that is the estimate of your MIMO channel matrix. So, this is basically the estimate of the MIMO channel matrix, or in fact we can write this as the LMMSE slash MMSE estimate of the MIMO channel matrix for the given problem. This is the LMMSE slash MMSE estimate of the MIMO channel matrix. This is 1 over 6 minus 1 over 600 minus 1 over 600 1 over 6. All right. So, for this example, this is the MMSE or LMMSE estimate. Of course, again do not need to repeat this very often, I have repeated this many times, that is LMMSE if the prior distribution, prior probability density function of the channel coefficients of H is non-Gaussian. The MMSE estimate if the prior probability density function is Gaussian, okay, and that has to be clear to you at this point. Okay. And now let us compute the error covariance. As I said, I do not need to separately compute the error covariance again, because I have already computed, it is a part of the calculation of the LMMSE estimate. Error covariance of your LMMSE estimate that is your expected value of H hat minus H into H hat minus H transpose, that is equal to, and we have already computed this, that is x transpose x divided by r sigma square plus I m divided by r sigma h square inverse, and this we have already computed. This is equal to 1 over 3 times 101 into 52 minus 49 minus 49 52. All right, this is the error covariance. This is the this is the error covariance. And also realize that this is an error covariance which is a 2 cross 2 Okay, we are looking at H hat minus H into H hat minus H transpose. So, the diagonal elements correspond to the error covariances of each receive antenna. So, in general look at this is H minus H into H minus H hat transpose. This is going to be T cross, this is going to be an M cross R, this is going to be M cross R matrix. Okay. So, this is M cross R matrix. So, each element is basically the sum of the covariances corresponding to each sum of the error covariances corresponding to each transmit antenna. If you look at each row, alright. So, each row basically corresponds to the receive antennas coefficients on the all the receive antennas for each transmit antenna. For instance, if you look at the first row corresponds to first transmit antenna, all the receive antennas, and when you do H hat minus H into H hat minus H transpose, you are summing across all the receive antennas. Therefore, is the sum of the each diagonal element if the is the sum of the variances corresponding to all the receive antennas for every transmit antenna. For instance, this 52, or if you look at, let me write this 1 over 3 times 1 cross 1 into 52 minus 49 minus 49 52, this is equal to, well, let me bring that factor inside, 52 divided by 3 into 1 cross 1 minus 49 divided by 3 into 1 cross 1 minus 49 divided by 3 into 1 cross 1, 52 divided by 3 into 1 cross 1, and what this is basically sum of variances corresponding to first transmit antenna, sum of variances of all receive antennas for first transmit antenna, and this is sum of variances of all RX antennas on second transmit antenna. All right. So, that is what we have. All right. So, this is an M cross R, this is an M cross M matrix. The error covariance that we have computed is an M cross M matrix. Of course, one can generalize this notion and compute the error covariance for a general, that is, remember, if you look at the MIMO channel matrix, we said it is an M cross R matrix. So, it has M R channel coefficients. So, one can compute the general error covariance matrix, which is MR times MR, that is, compute the error variance of each element and error, the cross correlations or the cross covariances of each, the covariance corresponding to each the covariance corresponding to each element separately, but here we are doing with simply computing the sum of the error variances of all the channel coefficients corresponding to each transmit antenna and all the receive antennas. Okay. So, that is the only difference. Of course, you can think a little bit about how to extend it to compute the error covariance of the MR, the net MR cross MR covariance corresponding to the error covariance corresponding to all the MR channel coefficients. All right. So, this example clearly illustrates how to apply the principle of LMMSE estimation to compute the MIMO channel estimate and also the error covariance of the MIMO channel estimate for the given example setup. All right. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.